My subject today is physics in 100 years. Now, of course, I don't know what's going to happen in physics for 100 years ahead. If I did, I'd be writing papers about it and gathering prizes for my insight. But I can suggest some broad areas that I think are promising that will play out over the next 100 years. And it's going to be a very exciting time that I can predict with confidence. I'll divide the talk into two parts. The first part, I'll talk about technologies. So these are challenges to improve life, if you like, to improve people's wealth, health, and perception of the world. And then in the second part, I will talk about improvements in understanding, in fundamental understanding in the next 100 years. What I see as the biggest problems, the biggest questions we have a chance of answering. So, technologies. It's a real challenge to talk about technology 100 years forward. If you put yourself back 100 years and try to imagine the technologies that are at the forefront today, it's a very humbling thing, and no one came close to doing it, and it's hard to imagine even a reasonable attempt. I mean, 100 years ago, people didn't know about quantum mechanics, and the understanding of matter was relatively primitive. So to get from there to understanding how modern computers work or modern communications would have been totally hopeless. I don't think we're missing anything quite so big anymore that's relevant to engineering, but still, it's a great challenge to have enough imagination to think so far ahead. Arthur C. Clarke famously said that a sufficiently advanced technology is indistinguishable from magic. So I'm going to think about things that I'm not sure exactly how we would do them, but we'd like to have them, and by some magic process, we'll get there. The first subject is making things at a very small level. We know, for instance, that if we want to have useful drugs, if we want to have materials that have good properties, if we want to have important chemical processes for making fuels or any number of other purposes, we want to work at the molecular level and know what we're doing. At present, that kind of work is done by chemists, but we have the equations that should allow us to do it by pure calculation, similarly to the way now aircraft are designed using computers instead of wind tunnels. So the reason that it's difficult is that the equations of quantum mechanics naturally live in spaces of very high dimension. The Schrödinger equation for n particles is a function in 3n dimensions. Nevertheless, we can hope to generate and understand that kind of data. It's especially nice to present it visually, because then humans have a way of thinking about it. So here's the kind of calculation we can do today of the electron distribution in a buckyball molecule, showing where the electrons are. We'd like to have, and this helps you design reactions for buckyballs and understand their properties. But we'd like to have this in a much more flexible and detailed way for many, many molecules, including larger ones. Once we can do that, we can not only think about individual molecules, but even start to think about how we can put many, many together to make useful structures and materials. These are not entirely dreams even now. This is graphene, a single layer of carbon atoms. It's very regular. This forms a very strong material that has many useful and remarkable properties, and we're just now learning how to work with it. It was only isolated a few years ago, and already we can see possibilities like making elaborate apartment buildings. These are actually filters that can shuttle materials from one place to another. Back in 1986 already, Don Eigler, working at IBM, pioneered the concept of moving atoms around using atomic force microscopes or atomic force apparatus, and to push atoms around. At that time, it was a very laborious process and very slow, and it still is much slower than it should be, although the technology has improved. On the other hand, the technology of printing things in 3 dimensions that are not tiny but larger has evolved into something that you can find in museum gift shops, or even hobbyists start to make very elaborate 3-dimensional structures using the so-called 3-dimensional printing, which is a process where you actually program in the shapes you want, and out it comes. What we would like to do then is scale that down and make it more efficient and more flexible, so that you can imagine 3D printers that make themselves, that make smaller scale versions of themselves. You get the idea. 3D producing materials through our mind, designing them through our minds, starting at the molecular level, understanding how the molecules fit together, using technologies to place them where we want, and making really imaginative machines that make other machines and allow us to efficiently sculpt the materials that we want to work with in powerful ways. So with that kind of technology, some targets are, we would like to make computers that are more like our brains in some respects. Current day computers are essentially 2-dimensional. They're on chips. That's because of the process by which they're made, by etching, basically. And that process is 2-dimensional. But of course, 3-dimension, if you could work in all 3 dimensions, you could make more denser and more powerful kinds of architectures. Current day computers are notorious, and chips are notoriously difficult and expensive to manufacture. They're built in extremely expensive facilities, multi-billion-dollar facilities with clean rooms where no human can trespass. And that's because if there are small errors, the machines can't fix themselves, whereas human brains are constructed rather, I wouldn't say sloppily, but they're very forgiving, and allow, bumps on the head, and different modes of operation, sleeping, there are all kinds of abuse without and yet they can still return to full function and even repair damage to some extent. So we'd like to have computers that have those capabilities, and even better than brains, and as far as self-repair, for instance. And we'd also like them, as I've already alluded to be able to assemble themselves and to reproduce themselves. The part of what makes human brains so powerful is the way they're made from many, many neurons, many cells, which reproduce themselves early on and proliferate in a baby's brain and have enormous numbers of connections. And the way that the baby and human learns is by strengthening some of those connections, getting rid of others. Very different, and interacting with the world, very different from the way we program computers generally, but we're learning that that's a very, very powerful strategy. And if we had machines that could embody it, that could lead in very interesting directions. And it's a challenge for coming generations. I think it's a worthy challenge for 100 years to make all that happen. So that's making things on a small scale, building up from atoms to modest size objects. We can also think big. And one pressing problem for the world today is that we use a lot of energy. Humans use a lot of energy, and at present, the sources of energy that we use, fossil fuels, are first of all getting exhausted, and secondly, they emit carbon dioxide and other pollutants, so they lead to many problems. Meanwhile, we're only using a tiny fraction of the energy that is impinging on us in the form of sunlight arising at Earth. That, if it was fully utilized, would correspond to about 40,000 times the human's energy use. So even a small fraction of it would serve. But if we want to think 100 years ahead, we may have larger populations. We may have more intense energy usage. We want to gather, in any case, our energy from the sun and perhaps more of it. Freeman Dyson proposed the idea of a so-called Dyson sphere, that an advanced civilization would surround its star with energy capturing devices and utilize all of its energy, so not just the energy, in our case, that impinges on Earth, but all the energy coming out from the sun. That would be a truly advanced civilization. However, we don't need anywhere near that. We won't be needing anywhere near that kind of energy density, energy flow in 100 years, and nor is it realistic to think we can do construction on that scale in 100 years. I don't think, but we can gather much more than we currently do, and we can put things out in space. We don't need to be limited by the Earth's surface. Another vision from science fiction, which is worthy of thinking about on 100-year timescales, is if you can make self-reproducing machines and have these processes of growth and exponential development, there's no reason why you couldn't have enormously large computers that are self-assembled, or better to think of enormously sized and powerful intelligences, so whole planet brains, or maybe that's too ambitious for 100 years, at least mountain-sized minds. Another thing that I think is much closer at hand, but I'm particularly interested in because it's fun and it's something that I've been actively working on, is the possibility of enhancing our senses using modern technologies. This is somewhat stimulated by comparison with a lowly but extraordinary creature, the so-called mantis shrimp. Human color vision is based on is called trichromatic vision. It's based on 3 different kinds of protein receptors whose light sensitivity curves are shown there. Roughly, these are not really accurate representations, nor are they to scale, as you see, but they give the sense of the thing. Whereas the mantis shrimp has not 3 samples, not 3 proteins, but depending on the variety of shrimp, somewhere in the neighborhood of 12 to 16. So somehow it's making use of that information, uh, and the lesson is that there's a lot more information in the electromagnetic signals arriving at our eyes or coming from the outside world than we use. And modern technology can allow us to get at that by having things like ultraviolet sensors down here or infrared sensors down there, or just better filtered receptors that will give us a richer view of the world. Now, there's a question of, so this is for instance, a vivid representation of what it would be to have 5-color vision. Now, there's a question of what our brains would do with that. How can you present that kind of information, which is easy to get from modern sensors, photosensors. You can certainly construct sensors that have this kind of response. How can you present that to the brain? And this is a long story in itself. Let me just show you the very first and crudest idea along that line. This is how the world looks to a colorblind person. If you may have seen the so-called Ishihara tests, where you're presented with pictures and you it's a test for colorblindness. If you're colorblind, you can't see the number that's in there. If you're not colorblind, then you can. And this is one of those tests, processed though to make us all seem colorblind. So there's a number hidden in here, but you can't see it if you can't tell the difference between red and green. But with the help of technology, you can take what was a two-dimensional degraded sense of colors and restore the information that was in the missing color by using the sensors we have, but imprinting time-dependent textures. And in this way, you can present extra information to the human brain in a form that it can use. So this is a simple, but I think impressive indication of the direction that I think will be very, very important, enhancing our perceptions using technology. Another important technology that I've alluded to in different ways in the course of the proceeding is the changing nature of minds and intelligence. So one thing that's happening all around us is that our sense of the world and our ability to control the world is becoming more distributed. So I can communicate, and I do routinely, with people around the world using Skype. This would have been unthinkable 50 years ago. So we can have presence around the world. I've had occasion also to be kind of presenting myself on one side of the world in the form of a robot that walks around and has my picture, and at the same time I'm looking as if I'm there and controlling this body. It's a remarkable experience, and I think it's one that's going to become widely shared and become more compelling over time, that our minds will be able to reach out to places all over the world, distant, interesting places. You could visit the Louvre. You could walk around and really experience it as if you were there. That's coming, and so so distributed intelligence, ability to affect the world, and ability to sense the world. Another frontier of physics is that's relevant to intelligence and the nature of mind, is the new kind of mind that's being developed through so-called quantum computers. The ordinary brains in the animal world are very sophisticated, of course, but their operation most, but not all physicists think can be explained, understood completely using classical physics. It's not an environment where quantum effects are likely to, the subtle quantum effects like entanglement and coherence are likely to be easily maintained. It's hot, it's wet, it's just not a friendly place for subtle quantum mechanics inside an animal brain. But we've learned that quantum mechanics generates a much denser description of the world than classical physics. Hilbert space is much larger than physical space, and so people have been thinking very hard and making progress on exploiting that space as a place for mind, a place for information processing. This is Google's superconducting quantum computer. At present, these machines are not very impressive as computing devices. They have only a few modules, or so-called quantum bits, but the rate of progress has been remarkable, and it's conceivable that in 100 years we'll have truly powerful quantum computers that are qualitatively different and more up to the task of computing things like molecular structure, as I mentioned earlier, because quantum computers will be very good at quantum mechanics. I couldn't help myself but to mention that one of the strategies for doing quantum computing uses a kind of particle called anyons that I named, and the idea is that as you move these kinds of particles around each other, the wave function that describes them in Hilbert space is processed in predictable and interesting ways that can allow you to build up elaborate calculations. And so this is a way of computing with knots. That's one of the most promising approaches to quantum computing. What would a quantum mind be like? Well, it's fun to think about, but it's a real challenge to understand quantum mechanics, and even as it applies to simple situations, to try to think like a quantum computer is really remarkable, because, I mean, it's really a stretch and really challenging, because a quantum computer, for instance, should be able to have a state of mind where it believes both yes and no is the answer to a certain question hypothetically, and do the parallel processing and let these different possibilities interact with each other. And quantum computers really, quantum minds would embrace contradictions. They could also manipulate time, because they'd be reversible. The quantum mechanics is reversible. You can move back and forth, and you could imagine a quantum computer, or for that matter, a classical computer, suitably designed to revisit its past, find states that it particularly likes, and enjoy experiences or states that are particularly rewarding for itself. So thinking about more powerful minds that are qualitatively different from ours, they're coming. What they would be able to do is really interesting. So now let me turn briefly to sort of more straightforward extrapolations of physics, the grand tradition of trying to bring together our understanding of the world that is powerful in different ways to make it a fully coherent understanding. So one frontier there is that at present, our description of the world divides into what I call force and substance. Technically, these are bosons are the force carriers, and substance are fermions. It's a very, very, to call one force and one substance is kind of an abusive language, but it gives some sense that in any case there are two very different kinds of ingredients that go into our description of nature these days. They are both described by the rules of quantum mechanics, but and at the level of having just one of them, they look very similar. But when you have groups of them, they behave very different, the bosons and fermions. So we would like to have a unified description where both bosons and fermions, the reason that both of them were described in terms of one underlying concept, and that concept would be two-faced, like the yin and yang. And we'd understand bosons and fermions as being things that one could interchange without doing violence to the equations. That's called a symmetry, and that would explain why there are two different things, and yet they are inevitably paired, because there is a transformation of the world that allows you to view it in either way, using either one as a stand-in for the other. Why should we believe such a thing? Well, it turns out that there's actually some evidence, not direct, but circumstantial evidence, we say, for the idea that this concept is true in the world. It's as follows. In our present fundamental theories, we have three different interactions that are based, and our theories of them in the so-called standard model are based on very similar mathematical ideas. Relativity, quantum mechanics, and something called gauge symmetry are the leading ideas. And they're so similar that, and I should say all of this is supported by mountains of evidence. The standard model is really, really reliable and heavily tested. So it's close to nature's last word, but it gives us a description of the world which is not only twofold in the sense of having force and substance, but also having different forces that look very similar but not quite the same, and in particular have different overall strength. And it's very tempting to think that that there might be one force from which all those derive, and that force, their commonality would be revealed if you extrapolated their strength down to much shorter distances or much higher energies, and if they came together, that would be an indication that really they are aspects of one unified force. The way to do these calculations is something called vacuum polarization, renormalization group. It's closely connected to what I got the Nobel Prize for, but I don't have time to explain it in detail. But the calculations, given the census of particles, we can do these calculations in an unambiguous way. And if we use only the particles we know about that have been seen in a laboratory, it almost but doesn't quite work. But the punchline of all this discussion is that if we boldly double the content of the world, as supersymmetry suggests we do, then they all come together really nicely. The extra particles that you need to implement this kind of possibility of flipping bosons into fermions and fermions into bosons changes the nature of how the couplings change with distance, and when you make those changes, it beautifully comes together. So that suggests that that unification is on the right, that those ideas are on the right track. And so far, that's circumstantial evidence. People are busily looking for the actual particles, but so far they haven't shown up. By 100 years from now, they will. Another big unification that we'd like to consummate, and we have come a long way, certainly in the last 100 years, and even especially in the last few decades, is the unification of small and large. Cosmology teaches us, Big Bang cosmology teaches us, that early in its history, the universe was a much hotter and denser place. In those circumstances, the basic interactions at high energies and short distances sort of come into their own. And these beautiful ideas about unification and symmetry govern what actually happened in the very early universe, if they're correct, and we can draw consequences from that. So our understanding of the very shortest distances and the very highest energies feeds directly into describing the earliest moments of the Big Bang, and it's those earliest moments where the crucial events occurred which control everything that happens later, including the present day distribution of galaxies, the creation of planets, and such. The ideas about microphysical physics that one applies to the early universe have been remarkably successful already. This is a picture of the early universe. It was very uniform, but if you multiply the contrast by 1,000, so that you can start to see the difference in intensity of the light coming from different directions from the very early universe, you find that there are patterns. These patterns later grow and produce, they are the things that produce structure in the universe, ultimately producing galaxies and so forth. Where did these fluctuations come from? Well, the leading idea is that ultimately they come from quantum fluctuations in the very early universe and then grow by gravitational instability, because when there's a little more matter, that by gravity accumulates more matter, and it's a self-reinforcing process, so things fragment and form structure. But you got to start somewhere, and the theory that seems very promising but needs to be fleshed out is that the origin of the fluctuations is precisely in the tiny domain of fundamental interactions and in the quantum fluctuations in energy that are occurring everywhere around us. At present, they occur, they're on very, very short time scales and very rapid, so our eyes don't see them. But in our calculations, we can reconstruct what's happening at very short distances and fast times. This is what's happening inside a proton. You have fluctuations in the density of energy in the gluon fields. This is absolutely crucial in understanding how protons behave. This visualization by Derek Lineweber is coming out of a calculation which gave accurate results of the mass of protons. So the origin of our mass is basically very much tied up with these fluctuations, and since the calculations reproduce accurately what we see, we can be quite confident that this is what's going on at very short distances and very fast times. There's a big target for the future, besides firming up the ideas we already have, making them more definite. There's something out there that we don't know. Astronomers have discovered through the study of motion of gas clouds, galaxies, and even that radiation from the Big Bang that I showed you, that there's a form of matter that's exerting gravitational forces. There's a lot of it, basically roughly 6 times as much of it as by mass as there is in the ordinary matter that makes up you and me. We know what it isn't. It isn't ordinary matter. The ordinary matter doesn't have the right properties. It's called dark matter. We don't know what it is, but there are very promising ideas coming from our explorations of fundamental interactions that produce suggestions for what the dark matter is that are consistent with observations, but suggest that the big challenge will be to make antennas sensitive enough to actually not only show that these guesses are consistent with the observed properties, but that they are these particles. I'm particularly fond of something called axions. That is an example of an idea, a particle, resulting in a particle that the idea was invented for completely different reasons having to do with fundamental interactions, but produces a particle that has just the right properties to make the dark matter. And we'll see. It's a big research frontier in physics today to design antennas to detect the axions that are out there, if the theory is right. And we'll see. I sure hope it doesn't take 100 years, but just to be conservative, and just because it's such a big problem, I included it in physics in 100 years. Final unification, and the last thing I'm going to talk about very briefly, but it would be criminal not to mention this as maybe the greatest frontier for physics and challenge for physics in the next 100 years, is to understand how mind emerges from matter, if it does. I mean, most scientists adopt the working hypothesis that understanding matter completely and how it's organized in brains will give you an understanding of how mind can emerge. Of course, we'll want to use other psychological concepts to describe how people behave, but we'd like to know the molecular that it's all grounded in molecular mechanisms, just as thinking machines, computers for sure, are grounded in molecular mechanisms, which we understand because we've designed them. Well, but brains don't look much like computers. They look like these complicated networks of interacting neurons, which are little computing devices, and we can sort of understand the individual neurons, but when you put them together into enormous networks, it's a challenge which has not yet been met to understand the properties of these networks and how minds and the functions of minds, such as memory, planning, abilities to calculate, all those abilities to speak, can emerge from these networks. So this is a huge challenge that I think will take 100 years at least to adequately meet. But in all this, we're understanding how the very basic interactions give rise to the large-scale structure in the universe that result in us, and then we look back and understand it. And here's the ultimate U for unity. We're trying to unify our understanding of the world and ourselves. Oh, thank you.